Hello, my friends. We're going to go over what entropy is and discuss the second law of thermodynamics. And we're going to go over some exam problems as well that might come up on a midterm and a final exam. So let's see if we can do this and be the greatest of all time at it. And thermodynamics it deals with the transfer of energy. So that's a key thing here in the second law of thermodynamics, where the energy is going. So the driving forces in thermodynamics involve entropy and heat. So entropy is this. Now, there's many definitions of entropy. So at first glance, it seems like things are becoming more disorderly, but it also, you can think of it as energy dispersal. So how this energy, and mass is energy, how this mass is being distributed. If it's more spread out, then it has higher entropy. We also think of it as having more something called microstates or more arrangements. If you can arrange molecules and atoms in different ways, then they're of higher entropy than if there's less arrangements, if they're more constrained in space. And heat is very much similar to that. So heat is not a thing. Heat is a process. It's the process of how energy is transferred. And it's the transfer of specifically kinetic energy, this bouncing around of molecules. And it's this bouncing around of molecules from a hot body, so a temperature that's hotter, to a body that's hotter to a body that's colder. That process, that transfer of kinetic energy, is called heat. And that's that transfer of energy is due to an increase of entropy as well, because we're now increasing the disorder of one of the bodies. We're kind of spreading out or dispersing, having a energy dispersal, so that kinetic energy is not constrained just to the hot body. It's now being spread out throughout both bodies, so we have more possible arrangements. So heat is this transfer of kinetic energy, which is also a result of increasing entropy. Okay, I hope that made sense. I hope that was very clear. So if you get that, then that's basically what the second law of thermodynamics says. So the second law of thermodynamics gives us a direction for all processes, and it says that the change in entropy total, or of the universe, I'll make them both blue, of the universe, and that's pretty vague, but we are going to break it down and go through some exam problems as well, has to be greater than zero. So entropy always has to increase for any real process. Now, the change in entropy of the universe, you might see it as the same as the change in entropy total. And by total, in thermodynamics, we usually break things down into two rough sections. So we have the change in entropy of the system, and sometimes you see it with a subscript sys, as in system, sometimes not, plus the change in entropy of the surroundings. And I'll just use SUR for the surroundings. So if you have like some system in here, the reaction's the system, everything else is the surroundings. The change in entropy of the system and the surroundings together combined has to be greater than zero. Okay, so this is the second law of thermodynamics, and to quantify this a little bit more, or I should say to add another equation so that we can solve more exam problems, using the thermodynamic definition of entropy for the surroundings, the change in entropy is equal to negative the change of enthalpy over the temperature, and this equation is the change in entropy of the surroundings. This is the change in enthalpy of the system. There might be no subscript. If there's no subscript, it means it's for the system. And it's negative because what's lost, energy, is heat. So this is the heat transferred from the system to the surroundings under constant pressure. And for the surroundings we can assume that there's no volume change or anything like that. If you wanted me to derive this equation, I'm very happy to do so. But we can quantify the change in surroundings pretty closely as the negative change in enthalpy divided by of the system divided by the temperature. So if we rewrite the second law, we can write everything in terms of the system. The change in entropy of the system, I'll just put system here for the enthalpy to make it nice, plus the negative, so this would be minus. So minus, change in enthalpy of the system divided by temperature has to be greater than zero. for any real process. Okay, so this is our other equation here. This isn't the second law. This is a derivation from the second law, but this is the main second law equation right here. Okay, so let's start off with some exam problems, and most of these are relatively easy. So what is the sign of the change in entropy of the surroundings when an exothermic reaction occurs? And notice the subscript is here. In higher level thermodynamics, you often see the subscript between the change and the S rather than afterwards, but it's more of a sign of kind of what you think is better or what's a little more accurate, but this just still means the change in entropy of the surroundings. So when an exothermic reaction occurs, the change in enthalpy is less than zero. So it's less than zero, so it's going to be negative. So if we want the sign of the change in entropy of the surroundings, of S, that's going to equal negative the change in enthalpy of the system divided by the temperature. Well, this is negative, right? This is negative, so this is negative. So here we have a negative and a negative number, making it a positive number. So the change in entropy has to be greater than zero. So it's going to be greater than zero. Does that make sense? Well, when the system is, let me draw a little diagram here. When the system is, the change in enthalpy is negative, what's happening is that this is exothermic, so heat is being lost. It's being removed. So if this is our system right here, we have energy being transferred as heat out of the system. The surroundings are getting hotter. They're not getting hotter, but they're absorbing this energy as heat here because the surroundings is like the whole universe. So we have energy lost to the system because it's negative. We have this heat transferred to the surroundings, so we're moving kinetic energy to the surroundings. That means we're increasing the entropy of the surroundings. So the change in entropy of the surroundings has to be greater than zero. It has to increase. The entropy of the system may likely decrease, but in the surroundings, it will increase. Okay, next one here. If the heat change in a reaction performed at constant pressure is equal to delta H, just like before, what is the heat change in the surroundings? Well, this one, again, this is a very easy one for us now because we have our equation. The change in the surroundings of entropy is equal to negative delta H over T. This would be, so if this is the heat change for the reaction or the reaction enthalpy of the system, it's just the negative of that. What is it of the surroundings? So this is literally kind of the answer to our question. Easy-ish exam problem. Cool beans. Okay, now here we're getting a little bit more challenging. When water boils, what is the sign of the change in entropy of the surroundings and the change in entropy total? What is the driving force for the process? Well, as you can see here, when water goes from a liquid to when it's boiling, we have more possible arrangements when it's in the gas phase, the gaseous phase. More possible arrangements, like kind of like more disorder, more microstates, more the energy, the mass is dispersed throughout a greater volume. There's a greater velocity profile of the gas compared to the liquid, where they're more kind of stuck together and their velocities are constrained. So we have a higher entropy of the system. Now, it didn't ask for the system, but we're going to need to know that. So when it boils, that's what's happening to the system. It's changed, the entropy is getting greater. Now, what about the surroundings? Well, if we have our water here, right, and we have some surroundings, say we're causing, I don't know, fire or something like that, we have heat transfer into the system. So the surroundings is actually going to be negative because we're pumping this energy into the system. So the kinetic energy we're using, or whatever it is, they could be thermal radiation, we're putting that away, we're taking it away from the surroundings. So the change in entropy of the surroundings has to be less than zero. Less than zero. So the surroundings, think of it as like more. It's hard to think of it as being more orderly in this case, but we're kind of we're compressing, kind of like we're localizing some of the energy from the surroundings into the system here. But overall, if water is boiling, this is a process. So the change in entropy total, even though it's equal to the change in entropy of the system plus the change in entropy of the surroundings, that always has to be greater than zero. Otherwise, this process won't occur. The change in entropy of the system, this has to be less than zero. No, sorry, it's greater than zero. Other way around, right? It's greater than zero. This one is less than zero, but they don't cancel out. So because the entropy change of the universe, or the total entropy change, is greater than zero, then this term wins. This is the driving force of the process. The change in entropy of the system is much greater than the loss of entropy of the surroundings. Okay, hope that made sense. Hope that was super clear. Okay, so what is next one here? What is the change in entropy of the universe if a system's entropy change decreases by 23 joules per Kelvin? So we have a number here. So this is of the system. I'll write system here. You don't, if there's no subscript, it means it's by the system. It decreases, so that's going to be negative 23 joules per Kelvin. And it loses, okay, we're losing 45 kilojoules of energy as heat. So Q equals negative 40, whoop, my pen's kind of jumping around on me. Negative 45 kilojoules of energy as heat at a constant temperature and pressure. Okay, so under constant temperature and pressure, this is also equal to the change in enthalpy. I've derived this in a previous video, but I can do it again if you want me to. Let me know in the comments. We want to know what is the driving force for the process. Okay, so we're not calculating anything, even though we're given all these numbers. We don't really need them, but we have a process. So a system, we don't even know what the process is, but let's say we have some state 1, some initial state. We'll just call it initial state, and it's going to some final state. It could be anything you think of. Initial state to final state. Well, as it goes this way, entropy decreases, right? So we have this, I'll do it in blue, decreasing entropy. Decreasing entropy. Yet the enthalpy is negative as well. So even though we have so we have decreasing entropy, and we also have decreasing enthalpy. And so they're kind of both decreasing in this way. I had to read it again. So this is decreasing enthalpy. So if this process occurs, what's causing this to happen? Is it the entropy or is it the enthalpy? Well, the second law of thermodynamics states, where is it? Way up here, states that the sum of the entropy in the universe has to be greater than zero. So we want the change in entropies to be positive. We want positive changes in entropy. Yet here we have a negative change in entropy of the system. So this decrease in entropy, this is going against, this is not going against the second law because we're not there yet, but this is not driving the reaction, essentially. It's not driving the reaction. We want the change in entropy of the system plus the change in entropy of the surroundings. We want that to be greater than zero. Now, if this is less than zero, see, this is less than zero, that's not helping us, right? That's not helping this process to occur if that's all we look at. So it's got to be coming from the surroundings. The driving force has to be from the surroundings. Now, so this is becoming a more orderly state, or we're kind of compressing things together, or we're going from a gas to a liquid. There's less arrangements, possible arrangements, less microstates. Anyways, this is not driving the force. This is not the driving force for the process. It has to be the change in entropy of the surroundings. But why is that? Why is the change in the surroundings greater than 0. This has to be greater than 0, much more greater than 23 joules per Kelvin, so that this whole thing is positive. Well, we have this enthalpy. Now, decreasing enthalpy means it's negative, right? Change in H is less than 0. The change in H is negative 45 kilojoules. So this is 45 kilojoules being released to the surroundings. And that's what increases the entropy of the surroundings. So if we have our system here, it doesn't have to be a flask, it could just be, I don't know, a box. And this is our system, and this is our surroundings. Now we have energy being released. This is exothermic. So the system is losing energy, and we have heat transfer out of the system to the surroundings, like this Q, and this heat transfer, we're transferring kinetic energy to the surroundings. So we're spreading out the kinetic energy, some kinetic energy in the system. We're not holding the kinetic energy in here. It's cooling down by spreading out and transferring heat, or having heat transfer, spreading out and yeah, heat transfer to the surroundings. Hope that's clear. I think I explained that like many times in a row, but I wanted this to be very explicit. You need to have a good understanding of this for the rest of thermodynamics to make sense. So because of this, we have an increase of entropy of the surroundings. And then we also have our other equation that we saw, the change in entropy of the surroundings using the thermodynamic definition of entropy equals negative delta H over T. Well, this delta H is negative, so this would be negative 45 kilojoules over the temperature. Temperature is always positive because it's in Kelvin. So our change in entropy of the surroundings will be 45 kilojoules over the temperature. And depending on the temperature, we could calculate what this is, but this is positive, and this whatever this is has to be more positive than this is negative, so that the sum of them is greater than 0. Okay, I hope that was helpful. We'll go through another one, couple more questions. In class, a substitute prof, maybe not a chemistry prof, said that processes occur to achieve the lowest energy. Why is this wrong? So processes occur to achieve not the lowest energy, right? We know that's it can't be the lowest energy because processes occur according to the second law of thermodynamics. So they occur to achieve the highest entropy of the surroundings. So it's got to be of the surroundings. So of the universe, of the surroundings. Of the highest surround of the universe total. Universe. There we go. Of the highest entropy of the universe. So the change in entropy of the universe, which is the same as the entropy total, that has to be greater than 0. That's why processes occur, not to achieve the lowest energy state. Actually, if I go up, now this system is getting lower in energy. This process is occurring, and the system's energy is decreasing. So this system is going towards a lower energy state because it's giving some of its energy to the surroundings. It's losing energy to the surroundings, so it is going into a lower energy state. But the energy is not lost. It's gained by the surroundings. So overall, the surroundings plus the system have the same energy. There's no change in energy for any of these processes. The change in energy is always constant. I don't know what grade you learned today, but for me, it was in grade 10 of my science classroom. It said the energy initial has to equal the energy final. Energy cannot be created or destroyed. It can only change form. So we can never get a lower energy overall. It's always going to be the same. Alrighty, so last one. This is a somewhat harder exam problem. It's maybe if you've been listening to this whole video, then it won't be hard at all. It should be easy peasy. So we'll jump into it. For the decomposition of H2, and we have a change in enthalpy of the system, because there's no subscript, equals 435.9 kilojoules per mole, and the change in entropy, standard change in entropy, that's what these superscripts mean. They just mean it's at 1 bar, kind of for standard state, equals 98.7 joules per mole Kelvin at 25 degrees Celsius. And we have our chemical equation right here. We want to calculate the entropy change of the system and the surroundings. So, well, system and the surroundings. Well, okay, well, this one we don't have to calculate. The change in entropy of the system is given directly. So that's nice. That's starting off easy peasy, right? 98.7 joules per mole Kelvin. And this makes sense. It's positive because we're going from for every 1 mole of gas that reacts, we get 2 moles. So we're kind of dispersing things out. We're getting more possible arrangements when we split the molecule up. Kind of more disorder spinning around in space, more possible arrangements. Okay, so this is positive, so that's good. Now the change in entropy of the surroundings, we got to go based off of this one, this change in enthalpy. So the change in entropy of the surroundings equals negative the change in enthalpy of the system divided by the temperature. And the enthalpy, we would make this in standard state, is negative 435.9 kilojoules per mole. That's pretty high. This is in joules per mole, and this one's in kilojoules. Usually enthalpy changes are in kilojoules, but anyways, 25 degrees Celsius, so we want that in Kelvin, 298 Kelvin. Alrighty, so we'll plug that into our calculator. Negative 435.9 divided by 298 is negative 1.4. How many sig figs? Three sig figs. Negative 1.46. So negative 1.46 kilojoules per mole Kelvin. So that's the change in entropy of the surroundings. This is of the system here. What are the driving forces? Well, this is negative and this is positive. So let's answer kind of B and C at the same time. So the change in entropy of the universe has to be greater than 0, and it's equal to the change in entropy of the system plus the change in entropy of the surroundings. So that's going to be equal to 98.7 joules. Now, remember your units, because look at your units and make sure they match up. This is in joules, this is in kilojoules. So now we got to subtract 1.46 times 10 to the 3 joules per mole Kelvin. Okay, so if we add this up, 98.7, so it's not so too confusing, 1.46 times 10 to the power of 3 joules is, now this is a negative number, right? 1361.3. Negative 1361.3 joules per mole Kelvin. And we have 3. We should have 3 decimal places. So negative 1360 joules per mole Kelvin. This is negative. So that means this shouldn't occur, right? This is according to the second law of thermodynamics. We're saying that if this reaction occurs this way, that's not thermodynamically favorable. It's thermodynamically favorable for the reaction to go the other way. So we want to go this way. And see this equilibrium reaction? This means that the reaction can go both ways. That means it's thermodynamically unstable for this reaction to go to the right, the decomposition to go this way, but it's thermodynamically stable for this reaction to go to the left. All right, so there you are. Hope you enjoyed it. Thanks for watching. I hope you get every single question right on the second law of thermodynamics. And I got many other videos on thermodynamics and other aspects of chemistry. Check those out with calculus or without calculus, also in math and physics. Thanks again. See you in the next video. Cheers.